Okay, so for this lecture, we're going to talk about Lagrange multipliers. Now, what are Lagrange multipliers? Well, really, it's just another way to solve optimization problems. This is most useful in problems with a larger number of variables. The idea is we introduce a new variable. Lambda, which I guess I'll phrase it this way, penalizes the equation for violating the constraint. Right? So with every optimization problem, there's always a constraint, whether it's just a domain issue in the equation itself, whether it's finding the absolute min or max of a function and you're given a closed interval. But in either case, if we're looking for an absolute min or max optimization, we need sort of a constraint of some kind. And this variable is going to punish us for violating the constraint. Now, what does that mean? And we'll discuss more later when we talk about how we can interpret lambda. But first, let's just deal with actually computing these things. So we introduce this new variable lambda. And then we construct a new function called the Lagrangian. Then we take partial derivatives. Then we solve a system of linear equations. Just like back in high school or middle school when you learned how to solve systems of linear equations. Okay, so all of this is fine, but really the best way to see it, as with many other things, is with an example. So let's say we start off with the following. Find the extrema of the function, and this is a utility function, a squared plus b squared, with constraints (0 less than or equal to a less than or equal to 50, 0 less than or equal to b less than or equal to 100, and 2a plus b equals 100. Okay, so we need all three of these things to be satisfied, and we want to optimize this, meaning find the min and max. That's essentially what we're doing. Okay, so we have the following steps. So we're going to work through them in order. First, rewrite the constraint equation to be equal to 0. So in this case, I'm going to have 2a plus b minus 100 equals 0. Right? Just change the equation so that I have something on the left equals 0. Okay. Then we construct this new thing called the Lagrangian. Construct the Lagrangian by subtracting the optimization function, Fn for short, by the constraint multiplied by lambda. All right, what do I mean by that? Well, we denote the Lagrangian by a cursive L, and we take U, the optimization equation, U minus lambda times the constraint, 2a plus b minus 100. Minus 100. So this is a squared plus b squared minus lambda times 2a plus b minus 100. Great. Okay. Now I'll start a new page here for this. Step 3. Set all partial derivatives equal to 0. Okay. Then solve for lambda. Okay. So I have the partial of L with respect to A, which I can denote as L sub A if I like. This is, in this case, 2a. Let's return back to the original function so we can see it. 2a. B squared is a constant with respect to A. And here the only thing that gets hit is this 2a times lambda. So it looks like I'm going to have a minus 2 lambda here. Minus 2 lambda. And I set that equal to 0. Okay? And I'll save the solve for lambda part once I have all the partials written out. Partial of L with respect to B should be exactly the same thing, just with B replaced, right? Oh, a little different over here because I don't have the 2 attached. So I'm going to have a 2b here. Of course, a squared goes to 0. And then I have a minus lambda, it looks like. So 2b minus lambda. And I set that equal to 0. And I'm going to stop writing set just because it's understood at this point. And now the only remaining variable is lambda, the new one that we introduced. And it turns out that every time I take this, it's just going to be this equation. Right? Because when I take the derivative of this with respect to lambda, I have this, which is a coefficient, a negative lambda. So that means that the derivative of this with respect to lambda is just the coefficient, 2a plus b minus 100, with the negative still on the outside, equal to 0. So I get negative 2a plus b minus 100 equals 0. This is the same thing as, this means same as, of course, 2a plus b minus 100 equals 0. And this is, of course, the constraint. So you should always have this guy, this dl d lambda, being equal to the constraint. This will always happen. Okay. So let's solve for lambda. This implies that 2a equals 2 lambda, which implies that, of course, lambda equals a. And over here, I simply get lambda equals 2b. Okay, so this is, remember from whenever it was that you learned how to solve systems of linear equations. When I have things like this, you can use, I think it was called the elimination method, which was, you sort of multiply something up here, multiply something down here, and then subtract and cancel something out and then solve. Or there was the substitution method. And what we're doing here is the substitution method, right? You're free to solve these in any way that you'd like, but it does turn out that the best way, in most cases, is to solve for lambda. This is the way that I would recommend. So all I do is I pick a variable, in this case lambda, and I solve for it in every equation that I possibly can. Okay. In this case, it's only the first and the second that I can do this. Oh, that's horrible. Okay, so I have expressions for lambda, and I'm going to write them out down here. Lambda equals a, and lambda equals 2b. So that means that a equals 2b. So I'm going to take this relationship now that I get from solving for lambda, right? If lambda is equal to 2b and lambda is equal to a, it has to be equal to, a has to be equal to 2b. And I'm going to take this and I'm going to plug it into this. And then I'll be able to solve for either a or b, depending on which substitution I make. From there, I can solve for lambda, and I can solve for the other one, whether I chose a or b. Okay, so plugging in here gives, let's say we substitute a equals 2b, just because it's already written this way. So I have 2 times 2b plus b minus 100 equals 0. Okay, so I get 4b plus b is 5b equals 100. So b equals 20. Great. Okay, if b equals 20, then what is a? Well, a equals 2 times b. This is 2 times 20, which is 40 in this case. Okay, so essentially what we've done here is we've found the critical points. So this is the multi-dimensional way of finding critical points. There's not one variable, right? This u function is a function in 2 variables, a and b. And we can't explicitly solve for one of them. So it's not as easy as solving and then taking a derivative, setting it equal to 0, finding the critical points. In this case, we use Lagrange multipliers. And this is sort of just the 2 or 3 or 4, or however many dimensional version of taking a derivative and set it equal to 0, right? Because all we're doing is taking derivatives in each variable and setting it equal to 0. So we're finding sort of that flat point in each dimension. Okay, that's at least the geometric interpretation of it. But now, so these are, I'll put this in parentheses or in quote marks here because it's not quite, but these are sort of the critical points. But there are other points I have to check to find extrema. I have to check endpoints, and I call them EP as well, right? So we have to find the outputs that correspond to the critical points, which we just found. This is a critical point here, a comma b, and the endpoints. What happens when a is equal to 0? What happens when a is equal to 50? What happens when b is equal to 0? What happens when b is equal to 100, right? So we have to check these things. Okay, So first, when a equals 0, notice that I'll remind ourselves of the constraint is 2a plus b equals 100, right? So when a is equal to 0, we can find out what b is. B is equal to 100. So this corresponds to the point 0, 100, right? Where this is the a coordinate, this is the b coordinate. Okay, how about when a is equal to 50? Then b is equal to 0. So this corresponds to the point 50, comma, 0. Okay, and then I guess we could check when is, because remember our range for b was 0 to 100. I could check when b equals 0 and when b equals 100. But you'll notice that we've already accounted for those, right? When b is equal to 0, a is equal to 50, and when b is equal to 100, a is equal to 0. So there's sort of a symmetry here, right? When a is at its extreme, b is at its extreme. When a is at its extreme, so is b, right? Okay, so these are the points I have to check along with the critical point, 40, 20, right? B is equal to 20, A is equal to 40, right? Okay, so now we just have to find U of each of these things, right? We take the critical point, or the location of the critical point, and we plug it into the function. Find out where is this maximized and where is it minimized. So I guess this is a step 4. We can call it. Plug in function, plug into the function to find max and min. Okay, so U of 0, 100 is 0 squared plus 100 squared. So this is 100 squared. 50, 0, 50 squared plus 0 squared. So this is 50 squared, 2,500. And if I plug in 40, 20, what do I get? I get 40 squared plus 20 squared. This is 1,600. This is 400. I get 2,000. Okay, so I've found my absolute max and my absolute min. So let's take a look at another example because I'm sure that not everyone understood that on the first go around, which is completely fine. This is something that a lot of students struggle with for sure. So if it's not immediately clear, it's not that big of a deal. But really, the calculus is not difficult. Right? I'm not doing a really hard calculus problem. I'm doing a really hard algebra problem, which of course is typically the hiccup here in this class. So let's do another one where we're finding extrema for the function q with variables kl, and that's going to be equal to k squared. I cannot write a k, it's embarrassing. K, it's a little bit better. K squared L to the third. Subject to the constraint 4k plus 5l equals 1. Okay, so let's remind ourselves of the steps. Rewrite constraint. All right, so I have 4k plus 5l minus 1 equals 0. Great, easy. Step 2, construct Lagrangian. Okay, so I have L of K L lambda, right? I write these just to emphasize that my three variables are K, L, and lambda. K squared L to the third, the original function, minus lambda times this version of the constraint, right? It's very important not to write this version here, right? I don't want this. All right, so I have 4K plus 5L minus 1. Great. Now I take my partials. And I'll just write equal to 0, right? Because I have to set them all equal to 0. I think I can fit this all on one page. DL, dk. This is going to be, L is just a constant, so I do power rule to the k. 2L to the third k. I write it this way just because L is a constant and so is 2, so I like to bring the constants out to the front. But you can have the L on the other side, it doesn't matter. Minus 4 lambda. And I'll set that equal to 0. Okay, well, let's do it with respect to L. Again, k squared is constant, so I bring the 3 down, I just do a power rule. I get 3 k squared L squared. Ooh, that's bad. L squared, sure, good enough. And I get a minus 5 lambda equals 0. And now, ooh, not that L. Script dl over d lambda. And remember, these are scripty d's because I'm taking partials. And I just get the constraint equation. Really, it is the negative of the constraint equation, but you can always just multiply both sides by a negative to, what am I doing? I can't talk and write at the same time, can I? Plus 5L minus 1. You can multiply both sides by a negative and still get the same answer. So it doesn't really matter here, but I'll leave the negative just to make it a little bit clearer. Okay, so now let's solve for lambda. Solve for lambda. Looks like I get 4 lambda equals 2L cubed K. Okay, so I have to divide both sides by 4. And I get lambda equals L cubed K over 2. Great. Now here in this one, I get 5 lambda equals 3 k squared L squared. And solving for lambda, I get, well, just 3k squared L squared over 5. Nothing really reduces there. Okay. So what does this together, let's write that a little bit differently. Let's say this along with this information here. What does this tell me? Well, this tells me that L cubed K over 2 is equal to 3k squared L squared over 5. Okay, because these are both equal to lambda, right? Equal to lambda, equal to lambda. Okay, so in this case, let's just first get rid of all the fractions. So I probably haven't left myself enough room here, but that's okay. I think I can make it work. L cubed K equals 5L cubed K, because I'm just going to cross multiply, equals 6k squared L squared. And then let's divide both sides by L squared. So I get 5LK equals 6k squared, right? Because I have L cubed here, L squared here. Divide this over and I'm left with just 1L. And now I can divide both sides by K. And in fact, I can solve for either K or L here. So I guess we'll make that decision now. So I have 5L equals 6K. And I might as well solve for L because it's already on the left. So I have L equals 6K over 5. Okay, so I'm going to circle this quick, not because I'm done, but because this is something important. I want to be able to find this when I'm looking back through my work. All right, so with this in mind, I can now take this constraint equation, which I'm going to start on a new page. So the important information is L equals 6k over 5. And what was it? 4k plus 5L minus 1 negative 4k plus 5L minus 1 equals 0. Okay, now I can multiply by a negative, and I give myself a 4k plus 5L minus 1 equals 0. And I'll make this substitution. 4k plus 5 times 6k over 5 minus 1 equals 0. Oh, look at that. Isn't that convenient? That 5 and that 5 are going to cancel. So I get a 4k plus 6k minus 1. So that gives me 10k equals 1. Right, just bring the 1 over to the other side. And k equals 1 over 10. Great. Okay, if k equals 1 over 10, what does L equal? Well, remember, L equals 6k over 5. So I just plug 1 over 10 into that to find out what L has to be. So this is 6 over 50 or 3 over 25. All right, so let's take a look at another example. Find the extrema for the function c equals 4k plus 5L subject to the constraint k squared L cubed equals 172,800. Sure. Okay, so step 1, I want to rewrite the constraint equation. So I have k squared L cubed minus 172,800 equals 0. Great. Next, I want to construct the Lagrangian. L, K, L, lambda. This is 4k plus 5L minus lambda times k squared L cubed minus 172,800. 3, I need to take my partials and set them equal to 0. With respect to k, I get 4 minus 2L cubed lambda k, and that will be equal to 0. With respect to L is 5 minus 3k squared lambda L squared, and that's equal to 0. And now finally the constraint equation. Negative k squared L cubed minus 172,800 equal to 0. Okay, so again, solve for lambda. I get 2L cubed lambda k equals 4. Divide by 2 gives me a 2, and then divide by everything that's not lambda. I get lambda equals 2 over L cubed k. Here I get, let's do the other way, 3k squared lambda L squared equals 5. Gives me that lambda is equal to 5 over 3k squared L squared. Okay. Together, these two give me 2 over L cubed k equals 5 over 3k squared L squared. which then gives me, if I just multiply both sides up, 6 k squared L squared equals 5L cubed K. Divide L squared over, divide K over, just like we did before, and I get 6K equals 5L. Okay, so again, we pick which one we want to solve for, and okay, in this case, looks like K is on the left, so we'll solve for K here. This is 5L over 6. Great. Now we take this and we plug it into the constraint. So let's do that. What are the things I need? I need K equals 5L over 6. And to remind myself of this, K squared L cubed. K squared L cubed minus, is it 172, 800? Let's see. Yeah, all right. So we can multiply by a negative, as always. It's an 8 equals 0. Using this substitution, I have 5L over 6 squared times L cubed. I can even write equals there and just do that all in one step. 172, 800. So that gives me 25L squared over 36 times L cubed equals 172, 800. So I get 25L to the 5th over 36 equals 172, 800. Okay, so now we have the question of what is L, and I'm just going to sort of wave my hands over this, and you can just trust that L equals 12. Of course, on an exam or on a homework or something, this would be something that, you know, is a little bit more manageable. But, right, so knowing what L is, I use the substitution here. So I have 5 times 12 over 6. All right, I can make this a little bit more manageable. 12 over 6 is a 2. So this cancels this and turns into a 2 up here. So this gives me just 10. Let's address the question. Oh, what happened there? Let's address the question. What does lambda represent? Well, the answer is a little complicated, but essentially, lambda represents something called shadow price. Now, I'm sure you'll learn about more about what this means in some of your business classes. But my understanding of it is that it's sort of an estimate of the price when there's nothing really on the market to compare it to. So the market doesn't give you a price. You sort of have to construct it on your own based on whatever estimates you may have. So this may be given to you. You may have to construct this on your own, something like that. But returning to, oh, can't spell. Returning to previous examples. If we return back to Q, we're looking at production. Q represents production here, with the constraint 4K plus 5L equals 1. That is the constraint of a budget. Returning to previous examples, so example 1 was talking about maximizing production Q equals K squared L cubed with respect to a fixed budget. Gee, I can't spell. Budget. 4K plus 5L equals 1, right? We needed our budget to be able to satisfy this for whatever K and L represent in this case. And with our budget being this exactly, how can we maximize production? That's the idea. Now, in this case, lambda represents the change in production with respect to a small increase in budget. Meaning, okay, if I loosen this constraint a little bit, right? If I change my constraint just a little bit and I allow a little bit bigger of a budget, how does that affect my maximum production? So of course, production will probably go up if my budget is allowed to be relaxed a little bit, if I have a little bit of wiggle room, right? If we return to example 2, I didn't number these, I probably should have, that's okay. We're looking for the extrema of this function, which turns out to be a cost function, subject to the constraint K squared L cubed equals 172,800. Now, K squared L cubed we saw in the first example represents production, and it does the same here. So example 2 was talking about this time minimizing cost, which was C equals 4K plus 5L, with respect to a fixed production level. K squared L cubed equals 172,800. Right? This says if this is my level of production, how do I find, or what is the minimum cost? What values of K and L give me a minimum cost? And that's really all that we're doing. And in this case, what does lambda represent? Represents the change in cost with respect to a small change, small increase, I should say, sorry. Keep it consistent, small increase in production. If production goes up, how does that affect the cost? That's the information that lambda holds. Okay, so let's do another example and we'll explicitly ask you to find the shadow price. Again, it's all gonna be the same process. The only thing is we're gonna have to find lambda at the end of it. Okay. Find the extrema. Extreme, looks like an E. And shadow price of f of xy equals x minus 4y plus 3, subject to the constraint 2x squared plus y squared equals 594. Great. Again, I'll follow my steps, rewrite the constraint 2x squared plus y squared minus 594 equals 0. 2, I have to write out the Lagrangian. X and y are my variables in this case. I'm still going to keep lambda. I get x minus 4y plus 3 minus lambda times 2x squared plus y squared minus 594. And now I start taking my partials. dl dx is 1. Remember, derivative of x is 1. Everything else goes to 0. I get minus 4 lambda x, and that's all my x terms, so I set that equal to 0. dl dy is negative 4 from this term, and a negative 2 lambda y from that term. And this, of course, should just be negative 2x squared plus y squared minus 594 equals 0. All right, solving for x, or solving for lambda. I get 4 lambda x equals 1, which gives me lambda equals 1 over 4x. Okay, and in this equation, I get 2 lambda y equals negative 4. So lambda equals negative 2 over y. What do these two give me together? Gives me that 1 over 4x equals negative 2 over y. So cross multiplying, I get y equals negative 8x. And I've already solved for one of them here. So this is the substitution I'll use in this part, and it looks like I can actually do it right here. So I'll just write equals, I'll drop the negative, I'll just multiply both sides by a negative 1, and that'll be gone. And I get 2x squared plus negative 8x squared minus 594, and I'll make that an implies, and I'll write equals 0 like that. Okay, so I get 2x squared plus 64x squared, which gives me a 66x squared. That's going to be equal to 594. And 594 divided by 66 turns out is 9. So this gives me that x is equal to plus or minus 3, right? Plus and minus here is important because it turns out here I get 2 extrema, right? So it's important not to miss one, is my point. Okay, so let's find the corresponding y values. Let's organize this a little bit better instead of doing that. Let's say when x equals 3, and I'll underline that, and then when x equals negative 3, and I'll underline this. Okay, when x equals 3, y equals negative 8 times 3, so this is negative 24. And when x equals negative 3, I get negative 8 times negative 3, which is 24. So the points I get are negative 3, comma, positive 24, and 3, comma, negative 24. Okay, so those are the locations of the extrema. And now we need to find shadow prices in this case, right? I'm going to underline that S there because I have 2 different points. They should give me 2 different values of lambda. So I'll organize my work here, and I'll say this is the work that corresponds to negative 3, comma, 24. And over here is the work that corresponds to 3, comma, negative 24. All right, so when x equals -3 and y equals 24, what does lambda equal? Well, I have a nice relationship here, so I'll just use this. Lambda equals 1 over 4x. I don't need to know y in order to find out lambda. So lambda equals 1 over 4x, and in this case, x is -3. So this is -1 over 12. And over here, I get 1 over 4 times +3. So lambda equals 1 over 12 in this case. So I'll box these as well as my answer. And that's the only different thing between what we did before and what we're doing now, right? All we're looking for now is, on top of finding the extrema, find the shadow price as well. Just find your respective lambda. But this is a nice example because you sort of, you run into a case where you have two critical points.